Hello everyone, my name is Jeff and I will show you how I exploited the challenge that is present at the end of the course. Just before we start, I want to precise something that I think is important. During this video, I will show you a path of exploitation that works. When you are learning, there will be many things that you will try that will not work, and you can easily be discouraged. You have to remember that every time you do something that doesn't work, you will learn why it doesn't work. So you will learn new things and you will get better, and that's the whole part of the process. Basically, you will just be as good given how many times you failed before. The second thing is that I will not explain what's already covered in the course. So if you didn't follow the course yet, there will probably be many things that you will not understand, and this is perfectly normal. Thus, the purpose of this video is more to show you what you will be able to understand and what you will be able to do just after you completed the course. Now let's see what's the program we want to exploit. It's a very simple C program that doesn't do anything besides making it vulnerable. There are two interesting lines, and the first one is this printf here that is having as the first argument what is received as a command line argument. As it is the first argument of printf, it is the format. So here we will be able to inject a format string that will be interpreted by printf, and that will allow us to print whatever is present on the stack at the moment of the execution. The second interesting line is the gets here, that is getting what it received on the standard input, and it is rewriting it in the buffer here. What's interesting is that the gets function doesn't check any size of input, so we will be able to write whatever we want of whatever length in this pointer right here. A little bit of presentation of the tools we will use. We will use the Pound tool set of library, which will allow us to make the writing of the exploit easier because it allows us to interact with the executable, to pass arguments, to write things on the command line, and to get the standard outputs. The advice I want to give you here is you should not use tools that you cannot write yourself. Unfortunately, what we will use here in Pound tools will mostly be covered already in the course. So you will know what it is. And when you know what it is, you can use a tool that simplifies the stuff, because let's concentrate. When you want to write an exploit, usually you want to concentrate about what's really difficult about it. It means really the exploitation, and that's all the things that is outside, like, okay, how can I redirect things inside the program, how I can do stuff like this. So it will allow us just to concentrate on the exploitation. Let's compile the file before we start. Here I will use the M32 option because I'm on a 64-bit system. If you follow the course, and I advise you to do it, you will install a 32-bit system, so you will not be required to use the M32 option here. And the next one is the Fortify source, which is another security measure. This one is will not be covered in this video, but I would advise you to make your own research just after you did this one. So of course we get a warning because you should never use the gets method. And now let's just try to run it. We will pass as the format, we will pass a %p, which will just take the values on the stack and write it as hexadecimal, just prepended with OX. So you can already see here that what we have at this moment on the stack is should probably be an address here, and then just the value 3. Now the next line that will be executed is the gets here. As the buffer is of 256 bytes, we will just copy a long string. So here I have prepared a list of 300 A's, and as expected, it's a segmentation fault. So what will be specific in this challenge is that we have 2 security measures that are enabled. The first one is the NX, which renders the stack unexecutable, which means that if we would be able to put a shellcode on the stack and we want to execute it, that will not be possible and the program will just crash. And the second one is the ASLR. It means that every time we will execute the program, the addresses, like we have here, the addresses of the program in memory will be different. So it means that we cannot hardcode the addresses. We will need to find another way to do it. So let's start to write the exploit. The pound tools is including a tool that will allow us to get a skeleton for the exploit we want to write. The argument is just to pass the binary. So let's put everything into an exploit.py file that is appearing just here. So the first line here is just importing the library. Here we open the executable we want to exploit. Here we have the way that the program will be executed. The first one is with GDB that will allow us to use directly GDB inside the exploit. So this will be very nice to make the debugging and the writing. And this is the way that the executable, when the executable is just executed as it is, it is the same thing that you can have if you execute the executable yourself on the command line. Here we have options for GDB that will be executed at the launch of the debugger. So here it's just a breakpoint on the main function, and then we continue onto it. This is where the execution of the executable is starting, and we get in return an input-output object, which we can use to pass things into the input of the program and to get the things that we receive from the output of the program. So this is the skeleton of the exploit that we don't need because we will write it ourselves. And the last line is interactive, which is basically we redirect the input of the output of the exploit directly in the executable, which means that we will be able to write things and to see the output exactly the same way as if the executable would be launched directly on a common terminal. The first thing we will do is just to make the test we did before manually. So at the execution of the program, the command that is passed as a command line argument can be passed just here. So we will do the same thing as before. We will just put a bunch of %p like this, and this is for when GDB will be used, and we will do the same thing when GDB is not used. What does the program? It just is printing something, so we will just print it ourselves. Here we can get a line with the reserve line function, and then we will send to it. It's the same as we putting something on the standard input. And what we will do is just pass 300 A's as before. And of course, we want to add a new line here because that's the way gets is knowing that it's the end of the input. Basically, gets is just reading everything until it gets a new line. And at this point, it stops and just writes everything that it got previously into the pointer passed as an argument that is buffer just here. To execute the program, we will use Python 3 because there are problems with the version 2 of Python. And here we are. So let's see. The first thing it does is it's writing a little summary about the executable we are loading. So we get the architecture, we get we see that the NX is enabled. We see that there is no stack canary. Stack canary is the security measure that we disabled just here with the D45 source. Then we see that the program is starting. Then we get the output of the printf. So as you can see, we should have five things separated by this. So it's exactly what we have. See, we have an address, we have 3, we have something else, then it's probably an address again, and probably an address again. And here we see that the program just received the segmentation fault, so we are getting exactly what we did manually just before. So now we can use another argument that is GDB, and this one is very nice because when we run it, it will just start GDB at the beginning of the execution of the program. GDB is already covered in the course, so I will not explain how to use it, but we will just go directly to how we can exploit the binary. So this is our main function. As we can see, we have the printf here, then we have a putchar. This putchar is already just the translation of the printf new line here. It's using a putchar because it's a single character. And then we have the gets function here. And we can already put some breakpoints. We can put the first one before the execution of printf, so we will be able to see exactly what's on the stack and see if that's in fact what we receive when we execute the exploit. And the second breakpoint, we will just put it before the ending because it will crash just after it, and we want to see what's happening just before. And here we are just before the execution of printf. As we can see on the stack, we already can see our format. So it's getting it right. And then we have other values that are present on the stack. And this should be what we will get on the output, because the first P here is referring to this, then the second P is referring to this. We can see if we just run the code. Now, what are we getting? And is it the same as we just got before? As you can see here, we have this address that is written here, then we have the 3 that is written here, then we have what looks like a pointer to the main, and then we have other addresses just here. So yes, it works. We're really getting what's in the stack. So this is a good news. It means that we will be able to bypass the randomization given by ASLR by getting the real addresses when the program is run. And here we have the next step. Just before the return of the main function, we can see that everything is just aces, and which is good because it means that we can have the control of EP, because as you know, the return function we have here, it will be getting the what's in the stack. It will be getting the address present on the stack and jump into it. And since it was written by us, then it means that we can control everything. We can control the return address, and if we can return the address, we can control, well, the execution flow of the program and just do whatever we want. But there is another difficulty. As you can see, it's not as straightforward as in the course, because if we disable the main function again, we can see that just before it return, there is this here. So it's changing ESP, and ESP is the place on the top of the stack where we will get the address. And here we cannot just, it's not just what is present on the stack at this moment, but it's what is present at the address pointed by ECX -4, and this address is what will be the new stack, and from this point we will get the address we want to execute. So this will be a bit tricky, but we will solve this problem later. But we can just see that if we want to control the return address, then we have to control ECX. And as you can see here at the moment, ECX is also overwritten with ACE, so no problem, we control it. So it means that the exploitation is perfectly doable at this point. And remember, last thing, that NX is activated. So once we will be able to get the return address, we cannot just put a shellcode and execute it, because that will make our program crash. Just before, we will need to render the stack executable again, and we will use the same techniques that is presented in the course. So for now, let's quit GDB. and start the exploitation. So the skeleton of our exploit will be the following. The first thing we will do is find where we can put our return address. So this will be the first step. Then the second step will be what can we put as a return address. So once we can redirect the execution of the code, what address do we want to put there? Then we will have the third step, which is render the stack executable again, not again, just executable. For this, we will use arrow P and mprotect. And then it will be execute the shellcode. So the first step, we can use pawn tools again because it provides us useful methods to find the offset. Another method is covered in the course. So for this, we can use the cyclic method, which the cyclic method is just we will get a string of length 300, such as when we will see what offset we are when we execute the program, we will know the offset comparative to the buffer pointer we have here. So this will just replace the ace that we put just before. We can write it so we can know how it looks like, and then we can send it to the programmer. Let's run it again with GDB. Okay, so this is what we send, and at the moment the program is crashing, we see that the ECX that we wanted to overwrite is containing OAAC. So we can already find exactly where we will put the value we want ECX to have. And this is the offset where there is the OAAC. To find the corresponding offset, we can just use the cycle find method. So if we do just a print of cyclic find, and then as an argument we can pass what we got just before, and executing, and we can see that we get 256, which makes sense. So this will be the offset that we can overwrite. So we can just start very easily to write the first step of our exploit, which will be we put something useless and we put 256 of it as we just got before. Then here we can put the value we want ECX to have. For this, we will use the P32 function that will encode the value we pass as we want it. It's the same as what's presented within the course with the pack method. So first we will put just something like this. And then the end of our exploit, remember to tell get that it's the end of the input. We put a command line here. And then we send it to the executable, and let's see what happens. So now that the program is started, we can just put a breakpoint before the crash and see if we got the good value in ECX, which is the case. As you can see, we just put what we wanted inside the ECX. So now the next step will be to put the address we want. So it's time to find all the addresses that we will need in order to make the exploitation. For this, we will need to use GDB, so we can really see what is on the stack and see how we can use this information in order to make the exploit. Let's put the breakpoint before we call printf, and this time we will see exactly what we have on the stack and how we can use it. So the first thing we want is we want to know what address is the buffer here, because that's where we write, and if we know what is the real address of this thing, then we will be able to put the address of the things we can write ourselves, and therefore to get the flow of the execution. This is what is present on the stack at the moment. We do the printf. You can use the VM map here to see what are the segments of the executable. So as you can see, we have the libc here, and we have the stack here. So this is the stack. We will write what we have right now. Of course, all those values will change every time the program is executed again. So what we want here is just to have the example values and to see how we can generalize those for the exploit. So here, for example, we have the start of the stack here. We can just, let's see, example base stack address. It's important for us to have the end of the stack also, because this will be for the next step. When we will use mprotect to render the stack executable, we will need to have the length of the segment. And we can get the length of the segment just by making the end minus the start. So in order to know the address of the stack, what we need is an address that is present within these addresses. If there is something like this on the stack at the moment we call the printf, then we will be able to leak an address. So let's see what we have. As you can see, this is what we have on the stack at that moment. And if we have something that is F, and then B, or a C, as you can see, it's contained within because the FFC13 here, it's just a little bit before the end address of the stack. So it means that the first thing we have on the stack is an address that is contained in the stack itself. And just by getting this, we will be able to know what's the base address and the end stack, because the difference between this address and the base address will most likely not change. Well, it actually will change a little bit, but we will see. But it will not be that by much. So we can really get the base address of the stack and the end of the stack address just by this example here. So we will call this variable leaked address. So as I said before, this will change upon every execution, but we will always get an address that is within the stack at every execution, even if the address will not be the same. Now we need the address of the buffer here, so we can know where what we write will be, what address we write will be. So how we can do it? Let's just disassemble main again, and this time we will put a breakpoint here just before we call gets, and see. The first argument will be the pointer buffer, and it's just here. So this is an example of, at this current execution, the address of buffer. Let's write it here. So of course this also will change every time, but what's good is that the difference between this address and the address of the stack will be constant. So the addresses themselves will change, but the difference with the address that we can leak from printf and this address, we will be able to get the real address just by a standard subtraction. Now we will also prepare the next step. That is when we will call the mprotect, or when we will need to use get that are present in libc. We will need to leak the address of the libc. So we can just see what we got here. Here you can see this is where we did our first breakpoint. So this is what is present on the stack at this point. And remember that we did a VM map here for the libc. So the segment that we are interested in is this one, because it's the one that is executable. So first we will save the offset, because this will be useful when we will get gadgets from the libc, because the real address will be present at the start of libc. We will add the offset. So this is the libc offset is here, and this will not change upon executions. Then will require the start. So this is the start of the libc, but of course, this address will change upon every execution. So here it's just an example that we can use to write the differences, but we need a way to extract the real address of the libc. And in order to do it, we can use the same method we used to leak the address of the stack. It is, we can just see what is on the stack when we call printf, and see if by any luck we have there an address that is present already inside the libc. So here the address of the libc is the f7db, and as you can see here, we have something inside the libc. We have the f7, and then we have db, so we just need to make sure that f7db is within the boundaries of the segment, and that's the case because it goes until the f7f. So here we have a way to leak the address of libc, which it is the 1, 2, 3, 4th. The 4th element on the stack will be a leaked address of libc. Leaked addresses are this one, and this is just the base address. So this is the base address. So now we can get our real addresses because we have all the informations that we need. We need the four first elements on the stack. So it means that we can just write here the 4 first elements because we don't need more. And the result we will get is something like this. We will get the leaked address of the stack as a first thing. Then we will have this column. Then we will have something random, that is the 3 that we don't need here. Then we will have something that we don't need just after, and then we will finally get the address leaked from libc. And the new line, because this is the new line that we will put by this printf that has been converted into a putchar in the real program. So the printf result is this one. We can print it, so we can easily debug it in case of problem. So the address of gets will be the first address we get from the printf. Here we get just the first 10 characters, and we precise that it's the hexadecimal format, minus the difference between, in our example, the real address of the buffer and the leaked address of the stack. So it's the leaked address minus the address we got before. So as you can see, this is just a way to get the relative difference. And we will use this relative difference with the address we really leak, which will give us the address from the leaked address. And we can write it in the console. Just like this. Then we want the base address of the stack. In order to get the base address of the stack from the leak address, we will just do as before. From the address we could leak, we will find the difference we got just in our example. But there will be a slight trick, because the difference between the leaked address and the base stack address will not be exactly constant upon each execution. It will slightly change. What we will do is that we will strip away the last three numbers here, so to make sure that we have 0, 0, 0, because the base address stack is required to end up with 3, 0. Of course, this method of just stripping away the last stuff can make that sometimes our exploit will not work, because, for example, imagine that the stack we leak is like ending with 4001. Then we will strip it to 4000, just like this. And then if we do that, we will get this as the base stack. But if this is the leaked address, then there is the more probable real base stack address is most likely this one. So this can pose some problem, and it means that our exploit sometimes will not work. There we can think of some methods in order to make the exploit more reliable, but we will not do this right now, and we'll just focus on the exploitation itself. So we can get we can just call it the row base stack address, which is the one we will get by the difference, and it's the leaked address. So the leaked address, as before, is this one, and we will subtract the difference between the leaked address in our example with the base stack address. So all this computation can seem a little bit tricky. So if you want to fully understand them, I suggest you to use GDB yourself, and then really to think about all those addresses are. You can even write some drawing of the memories that will help you to understand exactly how those manipulations behave and what they are for. So as before, we can just write something in order to make the debug. And now from this row-based stack address, we will just strip away the last 3 numbers. And we can do it quite easily just by using logic AND with the 5 first characters, 5 first numbers. We want to have the same, and then we will just clear the last 3, because as you know, the AND is just working like this. If you have something and something, if you have a 1, and then if you have something and 0, you have 0, and if you have 0 and something, then you have 0, and finally if you have 0 and 0, then you have a result of 0. So this means that the last one will always be 0, because we have a 0, and then the first bits will be a 1 only if they are already a 1. Finally, we want to get the address of the libc. So at first thing we want is to get the address from here. So we will not get this last part, because remember, we stripped away a p. And so we can just get it like this. So remember that it's ending with a new character. So in order to get those 10 characters, we need to strip away this last new line. So we want to begin at minus 11 characters and to stop at minus 1 character. And as before, it's hexadecimal. The libc leaked address will be this one. And then to have the base of the libc same method, we will use a subtraction from the example addresses we got just before. The leaked address minus the difference between the leaked libc address minus the base address. So the first one was the leaked. And that's it. So now we can see if what we got here is in fact correct, given what we can see using GDB. So let's just add another print here, and let's verify all those addresses. GDB, and we will put a breakpoint. Let's put the breakpoint. We will need to see if we have the good address for the buffer. So we need to find if the address we have here is the same, and then we will need to control that we have the right address for the stack and the right address for the libc. So let's put first breakpoint here that will allow us to to make debug if there is any problem, and then we will put a breakpoint here, and finally a breakpoint at the end of the program. So this is a printf, we don't really care right now, and this is the gets. And we can also use vmmap to show the addresses of the segments. So what do we have? What do we have? We don't need this anymore. Let's see what we have in comparison to, well, we have, okay, we have just, looks like we have a slight syntax error here. So let's start again. Breakpoint, printf, breakpoint, gets, and finally breakpoint at the end. And let's go and vmmap, and now we should have everything set up. This is what we get here. So the address of the buffer should be this one, ffc14 19b00. So as you can see, this one here is correct. And you can see that it's really different from the one we had before here. So we successfully got the real address. Then this is the base stack address, the row one, and then don't we have the, oh, maybe I forgot to write it. Let's check, and I just forgot to write it. So I will add the print here, but normally we should be able already to see it, because here we just strip the last three numbers. So if what we get from the row base stack, and then we just put the three last numbers away, should give us the real address. So let's see if that's the case. FFB, F9, FFB, F9. So this one has a problem here. We will see what's happening in a moment, and we will just see if the libc is working. So the libc we have here should be F7D11000. So this one is correct. So we just need to see why our stack address is not correct. So the difference we got just before between the real stack address and what we got from our computation was of 200 hexadecimal, 2000 hexadecimal, and we expected to have to adapt this value because, as I said before, it's slightly changing upon each execution. It looks like maybe we went in bad luck during our first experiment, and then the rounding is not right. So what we can do here is just to manually add, we'll add 800 is in hexadecimal, which is the same as if we were to add 500 upon 1000 in decimal. So it's the middle, and hopefully it will we can get the right stack address if we do that. So let's find out. Let's just find out, and we will be fixed very soon. Let's see what we have. So this is the stack address, and what we get here is, so we are still below. We are still below. We are still below. So we can try to add a bit more here. Maybe if we had this, let's check if it works. Let's see if it works. We can put a breakpoint and see what the address here. It's this one, and what we get. Now we have the right address. So okay, I'm not exactly sure about why the difference is so huge, because it should not exceed 1000. So maybe it's possible that I pasted the wrong address when I did this just before. So well, we can continue just like this, but of course, if you want to write an exploit that works every time, you will have to dig a little bit further into this problem. Now that we have all those addresses, we can continue to write our exploit. So we can just get what we had before and start from this. Remember that this here is the ECX, but if you remember correctly, the real address that will be our new EIP is the one that is present at the address that we put here, -4. So we can just start like this by putting the address of our buffer, because since we can put what we want in the buffer, it's the place where we can, it's the place that we want to put the EIP. It's within the buffer. So this is the address of the buffer, and it will also be our ECX -4. So basically, this is this is a bit tricky, because this is the address of the buffer, and at the beginning of the exploit, it's the address of the buffer. So upon execution, the first thing we will have on the buffer will be the exact address of the buffer. And this is what we want to put at ECX. So if you remember, we know that what is located at our buffer plus 256 bytes is what will be the content of ECX at the ending of our program. So our exploits can continue with, can just be like, this is the, we will have at the beginning of the exploit, we will have the address of the buffer, and then we will just fill with ACE the rest of the buffer that we don't need. So it's 256 characters, but we need to subtract what we just put here so that it will be, for example, for now we will have 4 bytes here, so this length will be 4, and then we will have this followed by 252 bytes here. After that, we will need to put the value we want from ECX. We can just reuse this again. What we want in ECX is the address of the buffer, but we need to add 4 because remember that the address we need is at ECX minus 4. So, and we want to end up by a new line. Let's see if it works. Let's see if it works by running GDB again and by putting a breakpoint just before the end of the program, and see if we have the address that we really want. Run. We are at the end. We have our ECX, that is this one. So this should be the beginning of buffer plus 4, because this here minus 4 should be the beginning of the buffer. So let's see what we had here as the buffer. We have the address of the gets right. It's 2C0. And here we have 2C4. So this minus 4 is what we want. So we just got the right address and we can follow the next step. So for the next step, we want, since we have the address now, but remember that the stack is not executable. So in order to get it executable, we will need to use the mprotect function that is located inside the libc. So we will need to use return-oriented programming in order to call the mprotect. For this, as mprotect requires 3 arguments, we will need to find a gadget that allow us to pop those 3 arguments so that they will not get executed as address of EIP. We will also need to find a single pop, because here at the beginning of our exploit we have an address, but we don't want to execute it. We want, because we can't execute it. What we want is to just go past this address and then execute code that is located in the libc. In order to find those gadgets, we will use the tool wrapper like this. And let's find out what the libc was by doing vmap into GDB. So this is the libc, and of course, if you use another version of libc, you will have to get the address of the gadgets that they will most likely change. So this is different for, or it should be different for every libc. Let's load the library. And find a pop gadget. So we need to find with the one that has no consequences. So this one is great because it just pops into EAX and then it returns. So this one will be our pop-get-get. Pop-get-get. This, and this is the offset relative to the libc base address. And you should not forget to add the libc offset. It should be libc that we found here. So in order to show you, remember that we are talking about this thing here. Now we have a pop-get-get, and we also need to find a pop because the mprotect we want to call is composed of 3 arguments. So find pop, and pop. First one is great because it's using EAX, EDI, and ESI, so it's perfect for us. Pop3 get. And same as before, we want to add our offsets. And I made a mistake just before. The offset we found using GDB must be subtracted. Now, what do we want? Also, we want the offset of the mprotect function. So to find it, we can use GDB again, use the xinfo command and mprotect. Here you have the offset just here. So this is the offset of mprotect. Remember that it can also change relative to what version of the libc you are using. Mprotect offset. And so the mprotect address is the mprotect offset plus the libc base address. And here we don't have to subtract the offset because the xinfo we used here is already taking it into account. Let's write our exploit by using what we had before. So this is ECX -4, but of course we cannot execute it. If we try to execute this thing, then it will just crash. So the first thing we want to put is a pop-get here. So what it will do here, when we are at this point, the stack will contain this. So it will pop this thing, and then it will go to the next step. And the next step is simply to call mprotect. So this here is the get right address. It's our buffer in C, and it's also ECX. Then our three arguments will be the address of the stack. This is the first argument of mprotect. the base address. Then the second argument of mProtect is the size, and the size, as we had before the ending and the beginning, we can just get this size by doing a subtraction. Minus the by stack. This is the size. And let's not forget to add the concatenation here, here, here. The last argument of mProtect is the mode, and the mode, it should be 7. Why 7? Because it's the value that we need if we want to have read permission, write permission, and also execution permissions. Well, of course, let's not forget something important. After mProtect, we want to put a pop here. We want to pop the 3 values because we cannot execute this. The next thing we want to execute is our shellcode. So we will just put the address of the buffer, and here we had everything that we had just here. So remember, this is the buffer here. It's the buffer, and the shellcode, we will put it just after this. This will be our shellcode. So here we want to put the address of our shellcode, and the address of our shellcode is the beginning, so it's this here, and we need to add all those here, since all of those values are of 4 bytes, and since we have 1, 2, 3, 4, 5, 6, 7, 8 of those values, in order to arrive just here, we need to add 4 multiplied by 8, which is the address of the shellcode. Now, what's the shellcode? This is the shellcode. That is a reverse TCP, which means that it will try to connect to an host, and everything that is received by the host will be interpreted as a command, and everything that is output will be sent back to the host. This is covered inside the course, so I will not go into the detail, but as you can see, we're basically just creating a socket. Then we are connecting to the host. That the host will be this IP address and this port, so we need to listen to this port. So let's do that right now by using netcat here and listening at the port 4444. So it's listening. It's listening here. Then it will try to connect, and then it will use the dup2 function to redirect everything that it receives through the standard input into the socket that is being connected to, and everything that it writes will be also redirected to the socket. And at the last thing it does, it will call the execvu function calling bin.sh, which will open a shell. So this assembler file of this shellcode has been compiled into this format that you can find right here. Of course, in the course, it's explained exactly how this kind of this code here can be transformed into this shellcode format. Just something to have in mind is that since the gets is using the new line character here, you cannot have a new line in our shellcode, and that's not the case here. So new line would be a 0 and an A, and as you can see, we don't have any 0A inside the shellcode. Let's put our shellcode here. See how it goes, because we should have everything. We have our server listening, so we can see. First, we will try to use GDB to make sure that we have everything set up correctly. We have an error here. Let's find out. We forgot the plus. Let's go right at the end, because that's where the interesting part is. So it didn't work. Let's find out why. It doesn't work because we have an error here. So the error is line 98, and it says that this is not defined because we just forgot to add this. Okay, so let's go again and put the breakpoint. And let's step. And here we are at the beginning of the exploit. So the first address we have, remember that ECX was overwritten, that at this address -4, which is just here, we will have our pop gadget here. So the buffer, and it looks like this is in the C library, and it's it's exactly the gadget that we used, the pop EAX. So for now, this is all correct. We can just step. Then we want to execute the mprotect. So see, we are here, and this is mprotect. So it looks like it works. This is mprotect. We just go out of the mprotect and see what's after. This is the pop3 gadget that we used here. And it looks like it didn't work. As you can see here, there is probably a problem with the arguments of mprotect. So let's find out. Let's find out also if the stack address we have is correct, because if it's not, then mprotect cannot work. Let's run, and let's find out the stack address that is just here. And what we do have here, as you can see, we are too high right now. So it means that maybe we had it too much. Let's see if just by 1000 it works. So this is the address of the stack. What do we have? Here we have the right address. So this is fine. Then we have the first pop. This is not that important. And let's see that if in mprotect we have the right arguments. So remember, the first argument we want is the address of the stack, and this is the address. It is the address of the stack. The second one is the size, so it should be around 28,000. Let's see if that looks good or not. 28 FFD C, yes, it's correct. And then the last argument should be 7 to say read, execute, and write, and we have it. So this is fine. Let's finish and protect. This is, as before, the 3 pop, and then we have the return. So see that the problem we had before was related to the fact that the address of the stack was wrong, and since we have the, remember, NX here is activated, so before it tried to execute things on the stack but crashed because it couldn't. Now that we just used the mprotect, and as you can see with a map here, the stack is now executable. So now we can execute whatever we put on the stack. And since we put our shellcode, that's exactly what we are executing here, because see that this is exactly what I showed you in the assembler file. It's still listening, and here we have the XOR and see the XOR, then the move AX, of course it's in hexadecimal, then we have the CDQ, and everything is just right. Let's execute it step by step to see if it works. So this is the first int here is the socket function. So let's just execute it. And remember that an interruption is in assembler, the result of the call will be put into EAX. So using GDB here, we can just see if it worked or not. Here EAX is 3, and that is exactly what would represent a socket number, because in case of error, it will be -1. So the socket creation was good. Then we will have the connect. And again, let's see what we have. We have a 0, which is fine because an error would be -1. The next step is the call to the dub2. So we will have 3 calls to dub2 in a loop. So this is the first one. As you can see, we have a 1, so which means that it's working. And then we have second call of dupe, and this one is not working. So why is it not working? Let's find out. Okay, so it's not that it doesn't work. It's because we are in GDB. We cannot, because we are in GDB, when there is the execution of the, just here you can see the exec VE function, since it's in a different process, it makes GDB crash. So it should work. The reason that we didn't see the 3 dub2 calls was just because I was going too fast. But as you can see in our, here we have a connection in Netcat. So it did connect, so it should work. The only reason where it would not work at this point is when we have the wrong stack address. So that's possible because, as we saw, there is a slight change, and so there is a chance that it doesn't work. But in order to find if it works, we can just now call it without GDB and see if we have something. So here, so let's find out now without GDB if it works or not. First, we need to make sure that we are listening on the port that we will connect to, and then we will just launch it and see if we get a connection, which is the case. So remember that the shellcode we did was redirecting everything that goes here to the program, and that everything that the program writes will be redirected here. Also remember that the last thing of the shellcode was to open bin.sh shell. So since it's the new process, and since it has been redirected, what our executable is doing right now is acting as a shell that is connected through this connection here. If you know where if you understand where I'm going, it means that here we actually have a shell. So let's see if that's the case. And yes, look like we do have a shell. Look like we can just write commands and get the output. And from there, we can do whatever we want. We basically have the access. So I don't know how you feel when you see this, but it's always like, you're doing a bunch of stuff, and you know that at the very end you will get a shell. But when you actually get it, it's like, wow, that works. It works. It's amazing. So guys, and maybe girls too, because why not having more girls that are able to do some hacking like this? And I hope you all enjoyed this video, and you saw how sometimes you struggle, because even if you know where you want to go, or even if you have the path that is already set up, you will still have some problems along it. But well, that's part of the progress, and that's part of how it works. Good luck in your learning, and good luck in your struggling, and keep strong, because motivation is everything. Bye bye.